Hi there, Mr. Sutton here, bringing you the AB Calculus 411 Extra Practice Number 1 solutions on L'Hopital's rule. To find the limit of this expression, we first kind of mentally see what happens if we plug in 0. We see we're going to get 0 right away in the denominator, and probably the numerator as well. So let's just play it safe and take the limit of each one individually. So limit of the numerator, as you plug 0 into this, cosine of 0 is going to be 1. 1 minus 1 is 0, and squaring that doesn't change the fact. So numerator's coming out to 0. Denominator, and I mean, even though we know what's going to happen, we have to write it out with limit notation to make it official. Limit as x approaches 0 of x is going to be 0. Since the numerator and denominator are both 0, we apply L'Hopital's rule. So we're going to take the limit as x approaches 0 now of the quotient of the derivative. So we're going to take the derivative of the top and bottom independently. In the numerator, we've got something to the second power. Derivative is going to be 2 times the something. So we have 2 times 1 minus cosine of x times the derivative of this inner function. Derivative of negative cosine is going to be positive sine of x. And in the denominator, derivative of x is going to be 1. All right, so if we plug 0 into the numerator, sine of 0 is going to be 0, and that zeroes out everything. Denominator is not 0. So this whole thing then is just coming out to 0. To find the limit on this one, we first quickly mentally evaluate what happens if I just plug in 2 everywhere. And if I do that, I notice I'm going to get 0 over 0. So let me write out that with limits just to make it official so I can use L'Hopital's rule. So we've got limit as x approaches 2 of 2 minus 2 of the numerator. And that definitely is 0. 2 minus 2 is 0. And then we have the limit as x approaches 2 of the denominator. 2 squared minus 4 also comes out to 0. So therefore, since I have 0 on the top and the bottom, I can use L'Hopital's rule. So I'm going to take the limit as x approaches 2 of the derivatives of these items here. So in the numerator, derivative of 2 minus x is negative 1. Denominator, derivative of x squared is going to be 2x. And if I plug 2 in now, I've got negative 1 over 4, which is our final answer. For this problem, I'm trying to find the limit as x approaches 0. Now, I can tell if I plug 0 into the denominator, right away I'm going to get 0. So let me just be safe and take the limit of the top and the bottom independently as x approaches 0. So limit of the numerator as x approaches 0, we've got basically 1 minus 1, because you have e to the 0 in both cases. So that's going to be 0. As the x approaches 0 for the denominator, sine of 2 times 0 is really sine of 0, which is 0. Since the numerator and denominator are both 0 for the limits, that means we can use L'Hopital's rule. So now taking the limit as x approaches infinity of the quotient of the derivatives, in the numerator, derivative of e to the x is going to be e to the x. Derivative of negative e to the negative x, well, that's going to be negative e to the negative x times a negative 1 for the chain rule. So that's actually plus e to the negative x. And down below, derivative of sine of 2x, that's going to be cosine of 2x times a tail of 2. So 2 cosine of 2x. Plugging 0 into each of these now, I've got, let's see, e to the 0 plus e to the 0 in the numerator. That's 1 plus 1, which is 2. In the denominator, we've got cosine of 0 basically, which is 1, but we're multiplying by 2 out here, so that's a total of 2. And 2 over 2 can be reduced to 1. To find the limit as x approaches 3 for this quotient, let's first see what would happen mentally if I plug in 3 for all the x's. So that would be square root of 9, which is 3, minus 3 is going to be 0, and then 3 minus 3 in the denominator would be 0. So that's bad news. We want to take the limits of these independently and show that they're both 0 officially, so I can use L'Hopital's rule on this. So let's see, limit of the numerator as x approaches 3. Again, we saw that's really square root of 9 minus 3, which is 0. Limit of the, as x approaches 3 of the denominator, 3 minus 3, also 0. So then using L'Hopital's rule, let's take the derivatives of the top and the bottom separately and put them back inside a limit as x approaches 3. So the numerator, this is really x plus 6 to the 1/2 power minus 3. So that's going to be 1/2 x plus 6 to the negative half, and then that 3 is just a constant, so it's gone. And then let's see here. We've got Derivative of x minus 3 downstairs, that's going to be just 1. So now plugging 3 in again, well, this is really 1 over the square root of 3 plus 6 with a 2 down there. And this 1 is just going to go away because you divide by 1 and the 1 is gone. So we end up with really 1 over 2 times the square root of 9 when all is said and done. And 2 times radical 9 is going to be 2 times 3, so 6. So that's going to be 1 over 6 when the dust settles. For this one, I'm trying to take the limit of this expression as x approaches 0. So I can see already I'm going to have 0 in the denominator. Let me just take the limit of these independently just in case this turns out to be indeterminate. So limit of the numerator as x approaches 0, well, that's going to be 1 over 5 minus 1 over 5, which is actually 0. And then limit of the denominator as x approaches 0, also 0. Because I have 0 in the numerator and denominator for the limit, I can use L'Hopital's rule. So taking the derivative now of the numerator, I can think of this as x plus 5 to the negative 1. So the derivative up there, and this is all going to be with the limit as x approaches 0, the derivative up there is going to be negative 1 times x plus 5 to the negative 2, like so. And then that minus 5, that's just a constant, so that becomes 0. Down below here we have derivative of x, which is just 1. And now plugging 0 into this, I can rewrite this as negative 1 over 0 plus 5 squared. And then that's just going to be negative 1 over 25. For this problem, finding the limit as x approaches infinity, since I'm approaching infinity, I'm going to choose my champion here. So in the numerator, I've got x squared. That's the fastest growing term up there. In the denominator, we have 3x squared. And then I can just reduce that to 1/3. For this problem, I'm trying to find limit as x approaches 1 of this expression. So I can see right away that I'm going to get 0 in the denominator if I plug in 1. Let me just take the limit of the numerator and denominator separately, just in case this ends up being indeterminate. So limit as x approaches 1 for the numerator, well, ln of 1 is 0. 0 times 5 is 0, so that whole thing is 0. And the denominator we already talked about, the limit as x approaches 1 for that one, 1 minus 1, is also going to give me 0. Since I have 0 and 0 for the numerator and denominator, I can use L'Hopital's rule. So let me take the derivative of each side of the fraction separately, and we'll still have the limit as x approaches 1 for this. So derivative of 5 ln of x, that's going to be 5 over x. And then derivative of x minus 1 is just 1. So plugging in 1 for x to take this limit, we just have 5 over 1, which is all just 5. For this one, I'm trying to find limit as x approaches 0 for this radical rational expression. Now I know I'm going to get 0 in the denominator. Let me just take the limits of the numerator and denominator separately, just in case I end up getting an indeterminate form. So limit as x approaches 0 for the numerator, well, that would just be radical 2 minus radical 2, which is 0. And then limit as x approaches 0 for the denominator. Let me just write it out officially with limit notation here. That's definitely going to come out to 0. Since I get 0 for both of these, I'm going to use L'Hopital's rule. So let me take the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. So in the numerator, this negative radical 2 right here is a constant. That's just going away as 0. But this expression with the 2 plus x, I can think of this as really being 2 plus x to the 1/2 power. Derivative of that is going to be 1/2, parentheses 2 plus x to the negative 1/2. And there's no tail to worry about because the derivative of 2 plus x is just 1. So it's a kind of an invisible chain rule. Now taking a look at the denominator derivative, derivative of x is just 1, so that's not so bad. And now if I plug 0 in here, I'm going to have essentially 1 over 2 times the square root of 2 plus 0. So that's going to be 1 over 2 radical 2, which really can't be simplified more than other than just making sure the radical's not in the denominator. But we don't really even need to do that, so I'm just going to leave this the way it is. On this problem, I'm trying to find limit as x approaches 2 for this expression. And I can see right away if I plug in 2, I'm going to get 0 in the denominator. So let me just take the limits of the top and the bottom separately, just in case. So limit as x approaches 2 of x cubed minus 8, the numerator, that's going to be 8 minus 8, which is 0. Limit as x approaches 2 of x minus 2, the denominator, also going to be 0. Since I get 0 in both the numerator and denominator, I can use L'Hopital's rule. So let me take the limit as x approaches 2 of the derivative of the numerator over the derivative of the denominator. So upstairs we've got 3x squared. Downstairs we got 1. And now plugging 2 into this is going to be 3 times 2 squared, or 3 times 4, which comes out to 12. For this problem, I'm trying to find limit as x approaches 0 of this expression. And I can see pretty quickly if I plug in 0, I'm going to get 0 in the numerator and also denominator. So let me just show that as limits so that I can use L'Hopital's rule and get to the bottom of this thing. So let me take the limit as x approaches 0 of x squared, and 0 squared is just going to be 0. Let me also show limit as x approaches 0 of my denominator, 1 minus cosine of x. Well, cosine of 0 is 1, so 1 minus 1, just to confirm here, is indeed 0. Since I get 0 for numerator and denominator, I'm going to use L'Hopital's rule. So let me take the limit as x approaches 0 of the derivative of x squared over the derivative of 1 minus cosine of x. So in the numerator, we now have 2x. Denominator, this is going to be just positive sine of x. And plugging 0 in here, I can see I'm going to get an indeterminate form again, 0 over 0. So let me show that in limit form, and I'll have to use L'Hopital's rule, hopefully just one more time. So limit as x approaches 0 of 2x is 0. And limit as x approaches 0 of sine of x, also 0. So using L'Hopital's rule one more time, we've got limit as x approaches 0 of 2, the derivative of 2x, over cosine of x. Definitely not going to be indeterminate anymore, so let's just go and plug in 0. So that's going to be 2 over 1, which is just 2. For this problem, I notice that I'm taking the limit as x approaches negative infinity, so I'm just going to choose my champion on this one and ignore slower growing terms. So in the numerator, we just have x cubed that we need to consider. In the denominator, it's x squared, the dominant term down there. Reducing this, we've got limit as x approaches negative infinity of just x. And then that's just going to go to negative infinity.